In this video, I really just want to extend the previous video by going over two problems that involve bounds. And so we're just going to get into what definite integrals look like with this inverse trig business. So the first one that I have is the, is the integral from 0 to 4 of 6 over the square root of 64 minus x squared dx. And so my hope first here is that you would recognize that this integral is going to be something that involves arc sine, because in the denominator we have a square root, and it's a constant squared minus a variable squared. Further, the top doesn't have anything that's going to enable us to do u substitution. So it looks like arc sine. I'm going to take some steps to set this up. We'll pull the 6 out, and I'm going to rewrite the bottom so that we can clearly see it as being a constant 8 squared minus the variable x squared dx. Now, note, this problem does not require u substitution. And the reason is that the place that I expect to see an x is just an x. If this had been 2x squared, or 3x squared, or x squared squared, then we need a u substitution. But because this is just x squared, we're in good shape. So I mean, really all I need to do is now take this integral, right? This integral, we've got 6 on the outside. This is arctan, I'm sorry, not arctan. I even said before it was arc sine of the variable x over the constant, which is 8. And I'm evaluating from 0 up to 4. Hopefully you remember how to work with bounds. We're just plugging in the top bound and the bottom bound. That's the fundamental theorem of calculus. So I have 6 arc sine 4 over 8, which means 1/2, minus 6 arc sine 0. And again, hopefully this isn't too big a deal. If you don't remember this inverse trig stuff, go back and watch the inverse trig video. Make sure you understand that. This means what angle gives you a sine ratio of 1/2. Remember we talked about that in that other video. That arc sine means they're giving you the ratio and asking for the angle. So what angle has a sine of 1/2? Well, the principal value of that is pi over 6. Remember, if you visualize your unit circle, a sine value of 1/2 is going to be right there. That's the short one. This angle here is pi over 6. It happens over here also at 5 pi over 6, but our principal values for sine were in the first and fourth quadrants, so that's why we pick pi over 6. Minus 6 times the arc sine of 0. So what angle has a sine of 0? That's this angle over here. That's an angle of 0, so 6 times 0. So all in all, our answer ends up being just pi. And that's it. We're done with that one. I have one more example for you of an integral that requires that has bounds, and it's also going to be one that requires u substitution. So we'll look at that one next. Okay, so the second example that I have is the integral from 1/2 to the square root of 3 over 2 of 1 over 1 plus 4x squared dx. Now again, I hope we take a moment to think about what this integral probably is. Right? In the denominator, we see a constant squared plus a variable squared. When you see two things squared with a plus in between them, it's pretty much going to be arctangent. Right? So just as we've done on previous problems, we start by rewriting it so that we can clearly see what's happening. This is 1 over 1 squared plus 2x squared dx. And I hope it's clear to everybody why this problem is going to require u substitution while the previous one didn't. The previous one only had x squared. Because this has something else in the position of the x, I need to do a substitution. So I'm going to do u equals 2x. It means du is 2 dx. That means 1/2 du is dx. So I will plug these things in. I now have the integral of 1 over 1 squared plus u squared times, and my dx is going to turn into 1/2 du, so I'm just going to pull that 1/2 out front. Now you'll notice that I've sort of conspicuously left my bounds missing. I'm supposed to have something here, and I'm supposed to have something here. And the reason I left them blank is I wanted for us to remember that we need to change our bounds. These bounds in the original problem are x bounds. Like, that's a bound of x equals the square root of 3 over 2, and it's a bound of x equals 1/2. Once we do this u substitution, I need u bounds. And the way that we do that is by plugging these x values into the u substitution that we used. So this bound is going to become u equals 2 times root 3 over 2. So that means u is root 3. That's my top bound. And this one becomes u equals 2 times 1/2, which is 1. And so that means that bottom bound is going to be 1. So now that I have my new u bounds, I can actually take this integral. And actually, furthermore, now that this thing is in an appropriate form, this now looks exactly like arctangent. I have my 1/2 from the front. The arctangent one is 1 over 1 times arctan of variable over constant. Right? So if I simplify that a little bit, I've got 1/2 arctan u, and this whole thing is being evaluated using my u bounds, the square root of 3 and 1. Some of you, I know, like plugging your x back in. Some of you like putting your 2x back in here. If you put 2x back in, just use your old bounds. But if you're still with u, use the new u bounds. So we're almost done with this problem. This is 1/2 arctan root 3 minus 1/2 arctan 1. Arctangent of the square root of 3 is pi over 3 minus 1/2. Arctangent of 1 is pi over 4. So I end up here with pi over 6 minus pi over 8. We can get a common denominator on these things by going through 24. That'd be 4 pi over 6 minus 3 pi, 4 pi over 24. Minus 3 pi over 24, and that reduces to pi over 24, which is our final answer for the problem. So that's all I have for videos on this. That's it. I mean, it really just comes down to recognizing those things and then being careful with the bounds if it's a definite integral. So I will see you guys in class. Please, please, please make sure that you guys try out some of these problems tonight. Go through and do a few of them to make sure you're getting the hang of it, because I want to make sure we're getting this clearly during class.